In the past, when it comes to double integrals, I've always given you some sort of surface. So this is our surface here. I would give you some sort of surface, and then ask you to integrate it over some sort of region. In this case, it's this region here. But now I have the right to give you a double integral looking something like this, without specifying a surface. So when this happens, you can imagine this as being a surface of 1. So you're integrating this region over a surface of 1. So what that means is this. What that means is you're working out the volume where the surface is at a height of 1. So this will give you a volume where you have a surface of 1. So hang on, what that means is this. Imagine you've got an area where it's 2 centimeters across by 3 centimeters. So it's an area of 6. So when you evaluate this, you're really working out the volume under the surface where the elevation is 1, where the height is 1. So what that means is this whole thing here is a volume. But the thing is, when you have a volume of a height of 1, you can use this number 6 to represent an area, because it's at a convenient height of 1. So the point is that technically this will give you a volume, but then because it has a height of 1, then you can use the number 6 to also represent an area. So what that means is we can use a height of 1 to represent an area of this. So now we have a new technique. We can use double integral, where if you specify the surface to be 1, then this whole quantity here can represent an area. So we can work out an area of something by using double integrals. So let me give you an example. So now we are going to work out this area here using double integral. So that really boils down to us evaluating this. It boils down to us evaluating this, where the surface is always at a height of 1. But let's forget about the 1. So now we can just integrate this with respect to y. So imagine there's a 1 here. Integrate it. It will give you y from x squared to x, from x squared to x. So now put this into here. Take away, put this into here. That will then give you this. And now integrate this with respect to x. That will then give us this thing here. That will then give us this thing here, and then that would then give you an area of 1 over 6. So this area is 1 over 6. So let's double check this by using single calculus. So single calculus, when you set this up in single calculus, it would be the integral. Well, you would get the tall of the two, the height of the two. So this would be x, and then you take away this height here. Take away x squared dx from 0 to 1, from 0 to 1. So this is in single calculus. So the area is given by this in single calculus, which is the same as this thing here. So so you can use double integrals to work out the area of this, or you can use single calculus. But then you might be wondering, what's the point of using double integrals when you can use single integral? The reason is because of this. In the future, we're going to move from double integral to triple integral. So in double integral, in double integral, your domain is the xy plane. So this is the region that you're interested in. Well, when you come to extrapolate it to 3D, to triple integral, the domain represents the 3D space. So you're going to have some sort of 3D solid, and then when it spits out the number 1, just like it spits out a height of 1 here, I don't care what this really represents. I'm just going to know that when you get 1 times whatever, the whatever is going to stay the same. So this thing here can represent a 3D solid. This thing here represents a 2D flat flat piece of paper, if you like. Here you've got a 3D solid. So you can use this same technique where it has an output of 1, and then this quantity here can represent the volume of a 3D solid. Here, this thing here gives you, this quantity here represents the area of the region that you're interested in. Here it represents the volume of the solid in which you're interested in. What that means is this: you in the future, when you move to triple integral, you have the ability to work out the volume of something complicated, of the volume of some complicated 3D solid. So in the future I will demonstrate it. Okay.